Welcome to today's problem discussion on LeetCode number 495, Teemo attacking. This problem focuses on simulating an attack scenario to determine the total time an enemy remains under a poison effect. We'll explore various approaches step by step, including brute force and optimized solutions. Let's dive in. In this problem, we are working with Teemo, a champion from the game League of Legends, who is attacking an enemy Ashe using poisonous darts. When Teemo shoots a dart, Ashe becomes poisoned for a fixed duration. If Teemo fires another dart before the current poison effect ends, the poison duration resets, meaning that the poison effect will extend from the time of the latest dart. Our goal in this problem is to calculate the total amount of time that Ashe remains poisoned, given the times that Teemo fires his darts and the fixed duration of the poison effect caused by each dart. The input consists of two parts, a list called time series that provides the times when Teemo fires his darts, and an integer duration representing the duration of the poison effect. The output is a single integer, which represents the total poison time. To better understand the problem, let's go over some examples. In the first example, we are given time series equals 1, 4, and duration equals 2. This means that Teemo fires darts at times 1 and 4, and each dart causes a poison effect lasting 2 seconds. At time 1, Teemo fires a dart, and Ashe is poisoned from time 1 to 3. Then, at time 4, Teemo fires another dart, poisoning Ashe from time 4 to 6. Since there is no overlap between the two poison intervals, we simply add their durations together, 2 seconds from the first dart and 2 seconds from the second dart. The total poison time is therefore 4 seconds. Now, let's look at the second example with time series equals 1, 2, and duration equals 2. Here, Teemo fires a dart at time 1, poisoning Ashe from time 1 to 3. However, he fires another dart at time 2, before the first poison effect wears off. This resets the poison timer, so Ashe is now poisoned from time 2 to 4. The total poison time is the span from time 1 to 4, which is 3 seconds. It's important to note that the overlapping poison from time 2 to 3 is not counted twice, we only account for the additional time beyond the current poison window. In the third example, we have time series equals 3, 8, 12, and duration equals 5. Teemo fires his first dart at time 3, poisoning Ashe from time 3 to 8. Then, at time 8, another dart is fired, poisoning Ashe from time 8 to 13. Finally, a dart is fired at time 12, poisoning Ashe from time 12 to 17. However, there's some overlap between the poison durations caused by the second and third darts. Specifically, the poison duration from time 12 to 13 is already covered by the second dart. Thus, we only count the additional time beyond this overlap. Adding these intervals together, 5 seconds from the first dart, 5 seconds from the second dart, and 4 seconds from the third dart, we get a total poison time of 13 seconds. To solve this problem efficiently, there are a few key observations to keep in mind. First, we need to carefully handle overlapping poison durations. Whenever a dart is fired before the previous poison effect wears off, we only add the additional time beyond the current poison window to the total. Second, because the time series list is given in non-decreasing order, we can process it sequentially in O, n, time, where n is the length of the time series. By iterating through the list and calculating the poison time for each interval between darts, we can efficiently compute the total poison time by summing up these intervals. This ensures that the solution is both correct and fast, even for the largest inputs allowed by the constraints. To solve the problem, we first considered a brute force approach. The idea here is to calculate the total poison time by iterating over each attack and checking how long the poison lasts for each dart. If two attack intervals overlap, we adjust the contribution by only adding the non-overlapping part of the second dart. This involves starting from the first attack and then checking every subsequent attack to see if it falls within the effective poison duration of the previous one. While this approach is straightforward, its nested iteration results in a time complexity of O, n squared, where n is the total number of attacks. This makes it inefficient for larger values of n, such as when n approaches 10,000. Additionally, it uses no extra space, resulting in an O(1) space complexity. However, the inefficiency of repeatedly checking overlaps makes this approach impractical for large input sizes. Now, to improve efficiency, we can use an optimized approach based on a linear scan. Here, the intuition is to directly account for how much poison time each dart contributes. If a dart is fired after the current poison duration has ended, it contributes the full poison duration. On the other hand, if a dart is fired within the active poison window, it only contributes the time between the two darts. This way, we avoid explicitly checking overlaps by simply considering the timing of consecutive darts. To implement this, we iterate through the time series array once, summing up the poison time based on these conditions. At the end, we ensure to add the full poison duration for the last dart, since it always contributes fully. This approach drastically reduces the time complexity to O(n), as we only make a single pass through the array, and it maintains a space complexity of O(1) by avoiding additional data structures. Its simplicity and efficiency make it highly scalable for large inputs. Another approach we considered is the sliding window technique. Conceptually, it's similar to the linear scan but involves explicitly maintaining a dynamic window to track the start and end of the poison duration. With this method, we use two pointers, one to represent the start of the current poison window and the other to track its end. As the window slides over new dart timings, we update the total poison time accordingly. This approach also achieves a time complexity of O(n), as it processes each dart only once, and a space complexity of O(1). However, the added complexity of maintaining window boundaries makes it less straightforward than the linear scan, and it doesn't provide any additional performance benefits. For these reasons, while the sliding window approach is functionally equivalent to the linear scan, it introduces unnecessary complications without any tangible advantages. The key insight that allows us to solve this problem efficiently is that the poison contribution from each dart depends on just two factors, either the full poison duration or the time difference to the next dart, whichever is smaller. Recognizing this eliminates the need to explicitly check overlaps, reducing the problem to a single pass through the input. The aha moment came when we realized that we only need to compare consecutive attack times to compute the total poison duration, which makes the solution inherently linear. Comparing the approaches, the brute force method, while intuitive, is impractical for larger inputs due to its O(n)² complexity. The sliding window approach, though efficient, introduces unnecessary complexity. In contrast, the linear scan strikes the perfect balance by being simple, efficient, and scalable. It achieves O(n) time complexity with minimal space usage, cleanly handling all edge cases, such as sparse attack timings or completely overlapping intervals. This makes it the most elegant and practical solution to the problem. To solve the problem, we first need to understand its core requirements. Teemo attacks Ash at specific times, and each attack poisons her for a fixed duration. If another attack occurs while she's still poisoned, the poison effect extends, but the total poison time cannot exceed the given duration for any individual attack. The goal is to calculate the total time Ash remains poisoned based on the list of attack times, time series, and the fixed poison duration. A brute force approach to solve this involves starting with an initial total poison time set to 0. Then, we traverse through the time series list to examine each attack. For each attack, if it's the last one, we simply add duration to the total poison time. If it's not the last attack, we calculate the time difference between the current attack and the next one. The poison time contributed by the current attack is the smaller of duration or this time difference. Finally, we return the total poison time after calculating the contributions of all attacks. The pseudocode for this brute force approach begins with initializing a variable, total_poison_time, to 0. We then loop through each attack in time series. If the current attack is the last one in the list, we add the full duration to the total poison time. For other attacks, we compute the time difference between the current attack and the next one and add the smaller of duration or this difference to our total. The loop ensures that overlaps between consecutive poison effects are handled correctly by preventing any double counting. At the end of the loop, we return total_poison_time, which gives the total time Ash remains poisoned. This approach works because it systematically evaluates each attack's contribution while respecting the constraints of the problem. The brute force method works effectively because it carefully accounts for overlaps. By iterating through each attack and applying the min, duration, time_diff operation, we ensure that no segment of time is counted more than once. This avoids overestimating the total poison time. There are a few important edge cases to consider. If time series is empty, the result is 0, since no attacks occurred. If time series has only one attack, the total poison time will simply equal duration. For attacks spaced farther apart than the poison duration, there's no overlap, and the contributions from each attack are additive. Conversely, if attacks are closer together than duration, the overlap is accurately adjusted using the minimum function. From a complexity standpoint, the time complexity of this solution is O(n), where n is the number of attacks. This is because we make a single pass through the time series list. Space complexity is O(1), since we only use a few variables to store intermediate calculations, without relying on any additional data structures. The key operations in this algorithm include iterating through the time series list with a single loop. This ensures that each attack is processed exactly once. To handle overlaps between consecutive attacks, we use the min, duration, time_diff calculation. This prevents double counting by only adding the effective contribution of each poison duration. For the final attack in the list, we don't need to check for overlaps, so we directly add the full duration to the total poison time. This step ensures the last attack is fully accounted for, as there are no subsequent attacks to consider. By combining these steps, the algorithm efficiently calculates the total poison time while adhering to the constraints of the problem. This implementation solves the Teemo attacking problem by calculating the total time Ash remains poisoned after a series of attacks by Teemo. The function findPoisonDuration takes two inputs, time series, a list of integers representing the times of the attacks, and duration, an integer representing the duration of the poison effect from each attack. The solution begins by checking if time series is empty. If there are no attack times, Ash is not poisoned, and the function returns 0. This is an important edge case to handle. Next, the variable total_poison_time is initialized to track the cumulative time Ash remains poisoned. The function then iterates through the attack times, stopping before the last attack. For each attack, it calculates the interval between the current attack and the next one. If this interval is less than the poison duration, the poison effects overlap, and only the smaller interval contributes to the total poison time. Otherwise, the full poison duration is added to the total. Finally, after processing all but the last attack, the function adds the poison duration for the last attack to the total. This ensures that the final attack is fully accounted for. The solution is efficient, with a time complexity of O(n), where n is the length of time series, as it iterates through the list once. The space complexity is O(1), because no additional data structures are used. This approach handles edge cases, such as no attacks, attacks spaced exactly at the duration, or overlapping attacks, making it robust and reliable for all valid inputs. This is the Java implementation of the Teemo attacking problem, equivalent to the provided Python code. It uses the same logic to calculate the total poison duration. The key differences include Java-specific syntax, type declarations, and the use of Java's math.min method instead of Python's built-in min function. The class structure and variable names are consistent with Java conventions for clarity and readability. Here, we're working with the first example to understand how the algorithm calculates the total poison duration. The input consists of two attack times, 1 and 4, and a poison duration of 2 seconds. We start by initializing the total poison time to 0. During the first iteration, we calculate the interval between the second attack at time 4 and the first attack at time 1, which gives us an interval of 3 seconds. Since the poison only lasts for 2 seconds per attack, we add the minimum of the interval and the poison duration to the total, which is 2 seconds. At this point, the total poison time becomes 2. Finally, we add the entire duration for the last attack, which is always fully applied. This adds another 2 seconds, resulting in a total poison time of 4 seconds for this example. Now, we move to the second example, where the attack times are 1 and 2, and the poison duration remains 2 seconds. Again, we begin by initializing the total poison time to 0. In the first iteration, we calculate the interval between the second attack at time 2 and the first attack at time 1, which is 1 second. Since the poison duration is 2 seconds, but the interval is only 1 second, we add the smaller value, which is 1 second, to the total poison time. At this stage, the total poison time becomes 1. For the last attack, we add the full poison duration of 2 seconds. This brings the total poison time to 3 seconds. This case demonstrates how overlapping poison durations are handled by only counting the non-overlapping portion. In the third example, we consider the case of a single attack at time 5 with a poison duration of 5 seconds. Since there's only one attack, there are no intervals to calculate, and we skip the loop entirely. Instead, we simply add the full poison duration for this single attack to the total poison time. This results in a total of 5 seconds. This example highlights the simplicity of the algorithm when there's only one attack, as there's no need to check for overlaps or intervals. To summarize, the algorithm processes each attack except the last one by adding the smaller value between the interval to the next attack and the poison duration. For the final attack, it always adds the full duration, ensuring that no poison duration is double counted. This approach guarantees that overlapping poison times are handled correctly while keeping the implementation efficient and straightforward. To analyze the time complexity of this solution, let's break down the operations step by step. First, the base case checks if the time series array is empty. This is a simple condition that executes in constant time, O1. Next, we have the main loop that iterates through the time series array from the first element to the second to last element. This means the loop runs n1 times, where n is the size of the array. Within each iteration, 3 constant time operations occur, calculating the interval between consecutive attacks, evaluating the min function to determine the poison duration for that interval, and adding this result to the cumulative total. Each of these operations takes O1 time, so the entire loop contributes O(n)(1) operations, which simplifies to O(n). Together, these steps show that the time complexity of the solution is linear with respect to the size of the time series array. After the loop finishes, we add the final poison duration to the total. Since this is a single operation, it also runs in constant time, O1. When we combine this with the loop, the overall time complexity remains O(n), as the loop dominates the total runtime. Shifting to space complexity, the solution uses only a constant amount of additional memory. This is because no additional data structures, like arrays or lists, are created during the computation. The time series array and the duration variable are inputs, so their memory usage doesn't count toward auxiliary space. The only variables we use are total_poison_time, which holds the cumulative poison duration, and interval, which temporarily stores the difference between consecutive attack times. Both of these are simple integer variables, so their memory usage is O1. In total, the space complexity of this solution is O1, as the algorithm only requires a fixed amount of additional memory regardless of the size of the input. To understand the efficiency of this approach, let's compare it to a brute force method. A naive solution might involve iterating over every unit of time and checking whether it falls within a poisoned interval. For example, for each attack in time series, you could mark all times from time series I to time series I plus duration 1 is poisoned. Once all the poisoned intervals are marked, you would count the total number of poisoned time units. However, this approach is highly inefficient because, if the total poison duration spans t time units and there are n attacks, you would perform O(t) operations for each attack. This results in a total time complexity of O(n*(t), which can become extremely large if t is significant. The space complexity of the naive approach is also inefficient, as you would need additional storage to keep track of all poison time units. For example, you might use a set or an array to store these intervals, leading to O(t) auxiliary space usage. In contrast, the optimized solution we've discussed avoids iterating over all poison time units. Instead, it directly calculates the contribution of each attack to the total poison duration using simple arithmetic. This eliminates the need for additional storage and reduces the time complexity to O(n), and the space complexity to O1. Finally, the big O notation for this algorithm is mathematically sound because it processes each element of the time series array in a single loop, performing a constant number of operations for each element. The additional operations outside the loop are also constant time, so they don't affect the overall complexity. For space, the algorithm's use of a fixed number of variables ensures that auxiliary memory usage remains constant, resulting in O1 space complexity. When solving this problem, there are a few common mistakes to watch out for. One frequent issue is forgetting to handle overlapping poison durations. If consecutive attacks occur before the poison effect from the previous attack expires, the poison times overlap. Failing to account for this can lead to overestimating the total poison duration. To fix this, you need to only add the non-overlapping portion of the poison duration for each attack after the first one. Another mistake is assuming that the poison duration resets completely with each attack. In reality, if the poison is already active and the next attack falls within the active period, the remaining poison time is extended rather than starting over. The solution here is to use the maximum of the current time and the end of the previous poison effect to calculate the new duration. Additionally, edge cases like having a single attack or attacks spaced far apart often go untested, which can result in logic errors. Testing with minimal inputs and extreme spacing is crucial to ensure your solution handles these scenarios correctly. Finally, an inefficient brute force implementation can be problematic. Iterating unnecessarily over all elements, resulting in n² complexity, can cause timeouts for large inputs. Instead, aim for a linear solution that processes each attack time in sequence for efficiency. Another common mistake involves off-by-one errors when summing up the poison durations. These errors often arise from mishandling indices or misinterpreting inclusive and exclusive ranges, which can lead to incorrect totals. To address this, it's important to carefully track the exact start and end times of each poison effect, ensuring that overlaps are not double counted. From an interview perspective, this problem highlights interval merging or overlap handling, a common pattern in many interval-related problems. For example, you might encounter similar logic in problems like merge intervals or insert interval. Developing a strong understanding of how to recognize and manage overlapping ranges is a skill that generalizes well to other questions. When discussing your solution in an interview, emphasize your focus on optimization. While brute force may be straightforward, it is inefficient, so aim for an O(n) solution by processing attack times and overlaps in a single pass. Also, be prepared to discuss edge cases, such as a single attack, attacks spaced exactly the poison duration apart, or attacks that all overlap. Finally, if you initially start with a brute force approach, make sure to explain why it's not ideal and how you transition to a more optimized solution. This problem also connects to several related problems that use similar logic for handling intervals. For instance, in LeetCode 56, merge intervals, you focus on merging overlapping intervals by identifying and combining their boundaries. Similarly, LeetCode 57, insert interval, requires you to insert a new interval into a set of overlapping intervals and adjust accordingly. Another related problem is LeetCode 252, meeting rooms, which involves checking for overlapping intervals to determine if all meetings can be attended without conflict. Finally, LeetCode 435, non-overlapping intervals, takes a different approach by solving for the maximum set of non-overlapping intervals, which often involves techniques to eliminate overlap strategically. Practicing these problems can help solidify your understanding of interval-based logic and prepare you for similar challenges. When approaching this problem, there are several strategies to consider, each with its own trade-offs. The brute force approach is the simplest to implement but inefficient for larger inputs, as its n² complexity involves iterating unnecessarily over all elements. This approach is not ideal for scenarios where n approaches 10,000. A better alternative is the optimized linear scan, which processes each attack time in sequence. Here, you calculate the non-overlapping portion of the poison duration for each attack and add it to a running total. This method achieves O(n) complexity, making it more efficient for large inputs, though it requires careful handling of overlapping intervals. Another option is the prefix sum variant, where you pre-compute poison durations using a prefix sum array and then derive the total duration from it. While this method simplifies summation logic, it uses additional space, typically O(n), which might not always be necessary. By understanding these approaches and their trade-offs, you can choose the one that best balances simplicity, efficiency, and space usage based on the problem's constraints. Great job! Today, we tackled an interval-based problem and discussed how to optimize the solution to linear time complexity. Keep practicing similar scenarios to strengthen your problem-solving skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!